Hello, welcome to another video. Now in this video what we'll be going I'll just briefly recap what we have done before. So in the previous videos we were looking at damped oscillatory motion and what are damped oscillations, and I told you that damped oscillations are when you have a pendulum placed in a medium. So that's why the damped you can say damped oscillations are any oscillations when you have an external resistive force which is acting on an oscillator. That external force can be due to air, it might be due to air, or it can be due to any different medium. That medium might provide viscosity, it might provide friction, and because of that viscosity or friction there is going to be an external resistive force. There will always be an external resistive force which is going to act on the oscillator, and because of this external resistive force the motion of the oscillator will be reduced. It won't move as it should move originally. So you will see that the motion has reduced, and because the motion has reduced, the oscillations will not be continuously going on with the same amplitude. In free oscillations we saw that the amplitude never changes, the amplitude is constant and the energy is constant, but now we see that the amplitude and the energy is going to change, and how exactly it will change, let us come to it in a moment. Now I said that there are two forces which will be working on this particle. One will be the restoring force, that is minus kx, and second will be the resistive force, that is minus r dx by dt, that is minus r dx by dt. Now what was the differential equation that we got? We got the differential equation was m d2x by dt squared plus r into dx by dt plus kx is equal to 0. So this is the differential equation for damped oscillations or a damped oscillatory motion. Then we tried and assumed a solution, and finally we got the solution as x of t. X of t should be equal to a1, which is some constant, e raised to this entire bracket multiplied by t, plus a2 into this entire bracket multiplied by t. And we were in the process of studying three different cases. So we tried and studied three different cases, and if you remember, we have already studied two cases before. We started with what is overdamped motion. Overdamped motion is where the damping force is much greater than the restoring force. See, that oscillator will have some kind of restoring force which wants to bring it back to its mean position, and the oscillations continue. Now the damping force which is due to the medium is going to oppose it. So if this is my oscillator, this wants to move, there is a resistive force which does not want it to move, and so you will see this kind of motion is called overdamped motion. We also saw some examples that overdamped motion is where we use in door dampeners, where the graph, if you remember, of overdamped motion is, if this is your displacement x, if this is your 0, this is your 0 position, or rather let me change this position here, I'll write this 0, and this is your time axis. Once you displace the particle, it will come back to its mean position very slowly. It will follow some kind of exponential curve, exponentially falling curve, and very slowly it will come back to its mean position. Okay, and on the other hand, we also studied critically damped motion, and we saw that critically damped motion is when when it comes to critically damped motion, the resistive force becomes exactly equal to the restoring force. The resistive force becomes exactly equal to the restoring force, and in this case the motion is slightly different. If again this is x, let's say this is your x, if this is your x and this is your time axis, now once it is displaced, it will come back to the mean position in the shortest possible time. See, the time that is taking is this much, whereas here the time is a large amount of time. So that is how you can compare that critically damped motion will be motion where the object very quickly come back to its equilibrium position. And the main highlight, the main thing that I tried to tell you in both these cases, case 1 and case 2, is that there is no oscillatory motion. No oscillatory motion at all. No oscillatory motion. So there will be no oscillations in overdamped motion, there will be no oscillations in critically damped motion. And in the previous video we ended with a question, do we ever get oscillatory motion in damped motion? Yes, when there is damping force, even then there is a chance of getting oscillatory motion, and that is the case that we are going to study today, where we want to study how, even though there is a damping force, there is still oscillatory motion, and how will it differ from the previous case where there was no damping force. So today we are going to consider this case where the damping force or the resistive force will be less than the restoring force. That means the restoring force should dominate and the resistive force should be less. Mathematically it is that determinant r square is less than 4 km or r square by 4m square is less than k by m. Alright, so let us take this particular case and let us see what happens. Okay, so let me start deriving this. There is a short derivation that we have to do, and let us look at the derivation. Starts with, we are assuming r square by 4m square is less than k by m. This is our assumption. Now let us look at the solution that we have. If you remember, the solution has a bracket. The solution has a particular term which is r square by 4m square minus k by m. Now we are saying this term is less than k by m. If this term is less than k by m, that means this entire term should become negative, because a smaller number minus bigger number should give you a negative number. Okay, if this entire term is negative, then the square root should by nature give you an imaginary number. So what I'm going to do is, I'm going to write this bracket as, see, this will first of all, let me write, this becomes negative. Now I will write this term as square root of r square by 4m square minus k by m is equal to I into, I is the square root of minus 1, and now I just write r square, now I have taken I outside, so this term should become positive, so I will write it as k by m minus r square by 4m squared. And now this particular term that I have, I am going to assume something. So let me just write this. This is very, very crucial for later. We'll come back to this term in a moment. And this term, k by m minus r upon 4m squared, we are going to call this as omega d. D is for damping. This is, omega is nothing but our angular frequency. We have already studied angular frequency before, but this particular angular frequency is when there is a damping force acting. That is why I have used a subscript d, omega d. What is the significance of this and all, we'll just discuss in a moment. Let us continue with our derivation. So now I think the solution can be written as, if you remember our solution was a1 e raised to minus r by 2m multiplied by small t plus, now I am going to write I omega d into t, because this entire bracket I am replacing by I omega t. So this second term will become I omega d into t, and similarly the second term will be a2 e raised to minus r by 2m into t minus I omega d into t, Now what we'll do is, we'll just separate these terms, because e raised to minus r by 2mt is common in both. I'm going to take it common. So just before taking it common, in case you still have a doubt, let me just expand this. E raised to a plus b can be written as e raised to a into e raised to b. So this term can be written as e raised to minus r by 2mt and e raised to I omega dt, plus second term becomes a2 e raised to minus rt by 2m into e raised to minus I omega d into t, Now this e raised to minus r by 2mt, this term is common in both, so I'll just write that as common. So this term I'm writing outside, e raised to minus r by 2m multiplied by t. In bracket I write whatever is remaining, that is a1 e raised to I omega dt plus a2 e raised to minus I omega dt. Alright, now you may remember that e raised to I theta can be written as, let me just recall that formula here. E raised to I theta can be written as cos theta plus, or rather I should write e raised to plus or minus I theta should be cos theta plus or minus I sin theta. So let me just substitute this formula here, and I will get this term outside the bracket remains as it is, e raised to minus r by 2m into t. In bracket I have a1, instead of this I am writing as cos of omega dt plus a2, a1 cos of omega dt plus sine of omega dt there should be I into sine of omega dt plus a2 into cos of omega dt minus I sine omega dt. This is what I get. This is what I will get. Now, what should be my next step? My next step will be, the term outside does not change. The term outside does not change. I am going to slightly rearrange everything, and I am going to take the cos terms together and I am going to take the sine terms together. So I should get a1 plus a2 multiplied by cos omega dt. This is the first term. See, I have taken this cos and this cos together, and I am going to take the sine terms together. So the second term should be plus I into a2 sine of omega dt. 1 minute. In bracket a1 minus a2 sine of omega dt. a1 minus a2 sine of omega dt, because this is a1 into I sine omega dt and this is a2 into minus I, so it should be a1 minus a2, and again I should be common, so I am taking I outside because I is common to both the terms. Now what do I get from this? I am going to assume, let a1 plus a2 I am assuming as sine phi, a1 plus a2 I am assuming as, rather I should assume as a sine phi, and similarly a1 minus a2 multiplied by I, this entire term I am going to assume as a cos phi. I think some of you might have recognized where we are going with this. And now, using this substitution, I am running out of space, so I'll just go to the next page. And in the next page, we should get x of t is equal to, the term outside does not change at all, e raised to minus rt by 2m. In bracket, we had a1 plus a2, but a1 plus a2 we have substituted as a sine phi cos of omega d into t, plus this second term becomes a cos phi into sine omega dt. Now I think you might remember that sine a cos b plus cos a sine b is equal to sine a plus b, so I can write this entire term as, and a is also common, so I take a outside, a into e raised to minus rt by 2m, a into e raised to minus rt by 2m. What remains inside is sine of omega dt plus phi. Now this is something that is very interesting. Okay, why is this interesting? I'll just write in a moment. This is the case where you are getting damping force as well. So this is damped oscillatory motion. What about undamped oscillatory motion? Do you remember the equation of motion for undamped oscillatory motion? In that case, we had a into sine of omega t plus phi. Now does this look similar? See, what is changing? This a is as it is. There is a new term that has come in, that is e raised to minus rt by 2m. So instead of a, you have a into e raised to minus rt by 2m, and instead of omega, you have omega t. What does this mean? This means that earlier your amplitude was constant. This was constant for undamped. Now your amplitude is reducing. It is reducing. And how is it reducing? It is falling exponentially. You see that the amplitude is falling exponentially. Amplitude is reducing exponentially, because see, a is multiplied by e raised to minus rt by 2m. R is positive, 2 is positive, m is positive, time is of course positive. So this entire term is reducing exponentially. And instead of omega, you have omega t. If you remember, omega was under root of k by m. But here, if you remember, now we have k by m minus r square by 4m square. So your earlier angular frequency is going to reduce. That means your frequency also reduces. Okay, now you might say that this is the angular frequency. What about the normal frequency? See, nu is nothing but omega upon 2 pi, right? Omega upon 2 pi. So your frequency should also become 1 upon 2 pi square root of k by m minus r square by 4m square. So your frequency is also reducing. Your nu is reducing, your frequency reduces, your angular frequency reduces, and your amplitude starts falling exponentially. Your amplitude starts falling exponentially. That means the basic what damping does to an oscillator is your amplitude is going to go on reducing, and your frequency is also going to go on reducing. And the graph, just before the graph, let me just show you something. Yeah, let us just compare this, because when you place things side by side, you can easily remember. In undamped oscillations, the displacement was given by x is equal to a sine omega t plus phi. Now the amplitude is replaced by a into e raised to minus rt by 2m, and your sine, your omega, this should not be p, this should be omega d, this should be omega d plus theta. It should be omega d plus theta. What was your omega? Angular frequency was square root k by m. Here your damped angular frequency is equal to square root of k by m minus some term. And what is this term depending on? This term depends on r. So r is again the coefficient of damping. If r is greater, your frequency will reduce to a large extent. If your r is small, your frequency will reduce to a smaller extent. So again, if your r is greater, your damped oscillations will fall very quickly. The amplitude goes down very quickly. If your r is less, the amplitude will go down slowly. Similarly, the frequency also changes. So what are the effects of damping? Effects of damping are the fall of frequency and the decrease of amplitude. The fall of frequency and the decrease of amplitude. And how does this graph look like? Let me just draw the graph. The graph looks something like this. Let's say this is your x-axis and this is your t-axis. This is your x, this is your t, this is x, this is t, and this is 0. This is the 0 of displacement. Suppose your phase starts here. So I am assuming that phi is equal to pi by 2. Phi is equal to pi by 2. Pi by 2. Now your graph will look something like this. Again, it is sinusoidal. It has to be sinusoidal. Why? Because your frequency, your displacement is given by a into e raised to minus rt by 2m into sine of omega d t plus phi. So again you are having a sinusoidal function, but now the change is this sinusoidal function is changing with respect to time, and how this amplitude falls is given by this curve, this deteriorating curve. See, the amplitude first is this much, but the second amplitude has reduced and the third amplitude has reduced even further. So the fall of amplitude is given by e raised to minus rt by 2m, or rather a into e raised to minus rt by 2m, and this sine function is represented by sine of omega d into t plus phi. So earlier, if you remember, for undamped oscillatory motion, your sinusoidal function was perfect. There was no change in amplitude, but here the amplitude goes on falling. So this is the main effect of damping on a system. When damping force is acting, its oscillations are going to go on reducing, and rather the amplitude is going to go on falling. So basically we have studied 3 cases now. We have studied 3 cases. Just let us quickly recap. The 3 cases are: we have overdamped motion. When the damping force is greater than the restoring force, no oscillatory motion possible. The oscillator, when you displace it, it will take its own time to come to its mean position, but no oscillations. Second case, you have resistive force. This is critically damped motion, where your damping force is equal to the restoring force. It will come back to its mean position in the least possible time. And the third case, and another very important case, is when the resistive force is less than the restoring force. So it is the restoring force that is balancing. When the restoring force starts balancing, when the restoring force starts dominating, you get some kind of oscillatory motion. And let me draw it once again here. So the oscillatory motion in this case is going to be like this. It keeps falling, and finally it stops. So first you get some oscillatory motion, and then the oscillations die out. So whenever there is a damping force, the oscillations will die out, and the amplitude goes on reducing exponentially, and the frequency is also less than the previous frequency. Or that is, when there is no damping force, frequency will be more. Now the frequency will be less. So hopefully you understood these 3 cases. In the subsequent videos, we'll study a little bit, we'll analyze a little bit further what happens to the energy, so on and so forth. Okay, so we'll stop here for this video.